Hi guys, today we are going to learn about the equivalent circuit of transformer. Okay, if you consider an electrical device, any electrical device can be represented with its equivalent circuit. Okay, so when can we represent the device with an equivalent circuit means, so to represent the device in the form of an equivalent circuit, we have some equations. If we have some equations describing the behavior of a device, okay, if we have the equations describing the behavior of the devices, then we can construct equivalent circuit. Okay, then we can construct equivalent circuit. Okay, by constructing the equivalent circuit, what are the advantages? Okay, so to modify the device or else analyze the device. Okay, only by analyzing, we can modify the device. Okay, so by using equivalent circuit, we can modify and we can analyze the electrical device. Okay, so this equivalent circuit is analyzed by using circuit theory. Circuit theory. Okay, so what we will do is initially we will find the equations describing the behavior of devices. Finding the equations describing the behavior in the sense, see, we have studied the transformer under no load condition and loaded condition with winding resistance, all these things we have studied. Okay, so by using these things we came to know about something about the transformer. Okay, so with the help of all these equations, now we will design the equivalent circuit, and this equivalent circuit is analyzed with the help of circuit theory. Okay, so according to this result, we can modify our transformer according to our requirements. Okay, so basically let us consider the transformer is having a primary winding, let us say having resistance R1 and reactance X1, is having resistance R1 and reactance X1, definitely which is having some number of turns. Okay, if this is V1, and this is the current I1, these are N1 number of turns. And these are, let us say, N2 number of turns, having, definitely the secondary winding is also having some resistance, let us say R2, and reactance, let us say X2. Okay, I2 is the current flowing through the secondary winding. I2 is the current flowing through the secondary winding. Here what we are doing is simply we are neglecting the exciting current. Neglecting the exciting current. See, let us say V1 dash is the voltage drop in these windings due to the current flow I1. What is V1 dash? V1 dash is the voltage drop. V1 dash is the voltage drop due to I1 current flowing through the circuit. In general, this V1 dash does not change. uh, It's not a matter. Even maybe it may change, but we'll consider does not change from no load to full load. No load to full load. Even though if it changes, a very small value it will change. No load to full load. And its magnitude, the old V1 dash magnitude depends on say maximum flux, that is phi, frequency and number of turns. Here the number of turns are N1, okay. Simply the EMF induced E1 is equal to V1 dash is equal to, what is the EMF equation of transformer? 4.44 N1 pi max into F. Okay, so the voltage drop in the primary winding depends on number of turns, flux and frequency. Okay, now whenever the transformer is operating under no load condition, over there we came to know that I0 is the no load current, which is having two components. One is magnetizing component of current and another one is iron loss component of current. Okay, so whenever transformer is under no load condition. Okay, so the equivalent circuit, now I am drawing the exact equivalent circuit. The winding is having resistance and reactance also. Resistance and reactance. Let us say R1 is the winding resistance and X1 is the reactance. X1 is the reactance. I1 is the current flowing through these parameters R1 and X1. See, the no load condition, I0 is the current flowing like this. Okay, so I0 results in I mu, magnetizing component of current, IW, iron loss component of current. So this is I mu, magnetizing component of current, and IW, iron loss component of current. This is called no load reactance and this is called no load resistance. Okay, no load reactance and no load resistance. Now this is I0 and this one is I1 dash. I1 dash is the amount of current flowing through the transformer when it is loaded to satisfy the flux produced due to load current. Okay, so these are the number of turns in the primary winding. these R0 and X0 are called shunt branch parameters or no load parameters. Okay, this is having N1 number of turns. Now this winding is having N2 number of turns. These two windings are separated by an insulating material. So these two are magnetically coupled, but they are electrically isolated. And the secondary is having resistance R2 and reactance X2. Reactance X2. The current flowing through these two branch parameters R2 and X2 is I2, and voltage appears across the load, let us say V2. Okay, so this is the equivalent circuit of the transformer. So whenever we refer all the parameters to either side of the transformer, what happens? See, referring all the parameters to either side of the transformer in the sense, now what I will do is I will refer entire equivalent circuit to primary side, referring to primary side. Okay, so when we are referring to primary side, what will happen? The transformation ratio K will come into picture. Okay, keep in mind that transformation ratio K will come into picture. Here the thing is, we are referring these secondary parameters to primary side. Nothing more than that. Referring the equivalent circuit with respect to primary side in the sense referring all the parameters to the primary side. Okay. So what is the primary side equivalent circuit? It is having resistance R1, it is common. It is having reactance X1, and shunt branch parameters are resistance and inductance. No load resistance, no load inductance. These two are the shunt branch parameters. With this, the primary winding parameters are completed. Now we have to refer the secondary winding parameters to primary side. Secondary winding is having resistance R2 and reactance X2 are transferred from secondary to primary side. Whenever we are referring the secondary winding resistance to primary, we'll write that one as R2 dash. Am I correct or not? So this is R2 dash and this one is X2 dash. Okay, these are same. R1, X1. The current flowing is I1 is the current flowing through these parameters, and here the current division will take place. No load component of current I0 shunt branch parameters. This is IW, iron loss component of current, and this one is magnetizing component of current. This is no load resistance, no load reactance. Here the voltage is V1. Voltage is V1. So now the secondary branch parameters are referred to primary side. Here we can get the EMF induced in the primary winding, that is E1. Now referring the secondary induced EMF to primary induced EMF in the sense it is E1 dash. we can write E1 dash is equal to E2 by K, where K is, what is K? K is transformation ratio. Transformation ratio. Okay. R2 dash. What about R2 dash? R2 dash is equal to R2 dash is equal to R2 by K square. Similarly, X2 dash is equal to X2 by K square, where K is the transformation ratio. Transformation ratio. Now, current I1 dash will flow to this winding. Why? Because here the current will flow through these series parameters is I0 plus I1 dash. As it is a series network, I1 dash will flow through the circuit and its magnitude is equal to K into I2. K into I2. And if a load is connected, load is having some impedance, that is, let us say ZL is the load impedance. ZL is the load impedance. That load is transferred to primary side, so we have to consider that one as ZL dash. So ZL dash is equal to excuse me, ZL dash is equal to ZL by K square. ZL by K square. Now the voltage appears across the load is V2 dash is equal to V2 by transformation ratio. This is the voltage appears across the load. Okay, so this is the equivalent circuit of the transformer when referred to primary side. When referred to primary side. Okay, so if you are going to refer the equivalent circuit of the transformer to secondary side, okay, we will see this one. So equivalent circuit of the transformer when referred to secondary side. When referred to secondary side. Referring to secondary side in the sense, will not touch the secondary side parameters, that is R2 and X2. These are having a load, that is ZL is the load impedance. ZL is the load impedance and voltage appears across the load is V2. Voltage appears across the load is V2. Okay, that's it. Now, when referred to secondary side in the sense, we are transferring, what we are doing is we are transferring the primary parameters, primary resistance and inductance to secondary side. So primary resistance, that is transferred to secondary side in the sense, that is R1 will be R1 dash and X1 will be X1 dash. R1 will be R1 dash, X1 is X1 dash. So what is R1? So what is R1 dash? R1 dash is equal to R1 into K square, where K square is the transformation ratio. X1 dash is equal to X1 into K square. X1 into K square. And next, the no-load component of current I0 will be I0 by K, because it is transferred from primary to secondary side. Similarly, the resistance R and Ex. This is R naught is transferred from primary side to secondary side, then it will be R naught dash. R naught dash is equal to A square into R naught. Already we have discussed about this transformation ratio clearly in the last videos. And x naught dash is equal to A square into x naught. Okay. So this is the primary circuit, that is all the parameters are transferred to secondary side. What about initially the voltage is V1, and when this V1 is transferred to secondary side, that will be A into V1. A into V1. Now what is the current flowing through these two parameters? That is I2 dash, which is equal to I2, which is equal to I1 dash by K. K is the transformation ratio. So here in the secondary winding, EMF induced is E2. EMF induced is E2. The primary EMF is transferred to secondary side, that is A into E1. A into E1. So this is the equivalent circuit of the transformer when referred to secondary. Thank you.